there, ATS EVS 533 students. Dr. Shragi here, and I'm just going to give you a quick look at the interesting subdiscipline of Paleoclimate, which comes to us from the IPCC reports in Chapter 5 of AR5. This can be about Paleoclimate, the climates of the past, and how we can know something about Paleoclimate and what it can tell us about the climates of the future. It's a good challenge to wonder, what could we possibly actually know about the climates of the past? What kind of observations actually exist? What kind of inferences can we actually make about the climate of the past based on whatever information we have? Now, this actually kind of leads into a more philosophical discussion of what kind of observations exist in the first place. I'm going to tell you that an analysis, a breakdown of this that I like to use is to say that there's actually, in the science of climate studies, there's 4 different kinds of observations. We're calling them the satellite record, the instrumental record, historical record, and paleo proxies. And we'll talk about each of those in quite a bit of detail, or to greater or lesser extent anyway, in the next few minutes. Satellite is certainly a very useful way to study the climate of the recent past. We've actually been using satellites since the 1960s to do meteorological work, but it really wasn't until about the 1970s, late 70s in particular, so 1978 and 79, that we really started globally archiving satellite data and trying to make sure that different satellites up there had instruments that were a good match, so that there would be, when a new satellite went up, it had similar wavelengths, similar channels that it worked with compared to previous satellites, so that there weren't such big inhomogeneities in the data, etc. Really, global coverage and permanent archiving of meteorological data didn't really start until about 1979, but that is getting to be, 35, 36 years ago. Which means we can start having things like a satellite climatology of different meteorological parameters. And this isn't just about the images that those satellites collect, although the images are obviously valuable too. We can use remote sensing from the satellite to do things like infer the temperature or the winds or something like that, ice cover, etc. from these images or from these sensors. But there is a limit to how far back we can go with satellite data, and it doesn't really meet our idea of what we're going to be meaning when we're talking about paleoclimate. Now, the next set of information would, of course, be the the instrumental record. These are observations that come from like thermometers and other in situ observations. This could be things like pressure observations from early barometers. This could be observations of the length of glaciers or ice cover or something like that. Depending on the kind of information we're talking about and where in the world we're talking about and so on, these observations exist, and they can go back as much as a few centuries, especially in places like European centers of learning. Voyages of discovery certainly had, like in the 1800s, there were a lot of these voyages of discovery where they make measurements of things like, water temperatures or, or sea ice coverage or something like that. But they tended to be, they sailed someplace, they measured it, and they sailed away. They didn't maintain continuous observations on these locations in this instrumental record. Which makes you wonder how we can come up with data that look like this. I mean, this is the last, about 12,000 years of global temperature data presented in terms of a temperature anomaly. And, oh my goodness, there's something very interesting going on here with this big temperature change right here in the last 100 years or so. But how do we know all this? Or, for that matter, if we want to go back a few 100,000 years and track the global temperature anomaly, in this case, compared to that, with the dashed line there, the carbon dioxide in the atmosphere at the same time, how do we get that? Or if we want to go back a few odd million years and look at the global, this is a proxy for temperature data. It happens to be the ratio of certain oxygen isotopes, which we will talk about in just a few minutes. But how do we get that? Where does this come from? Not to mention, if we want to go really far back, here's about 70 years of global climate temperature anomalies. And, we can see that there's a surprising amount of structure here. We know something that happened about 56 million years ago. This is the PTEM, the Paleocene-Eocene thermal maximum. We know all kinds of interesting features. We can also see the general downward trend in the last 50 million years and so on. What is all of this? How do we get any of this information? Well, clearly, if you go back more than a few hundred years, what we need is some kind of proxy information. Proxy means, it takes the place of or whatever. Humans leave records that can be used, which were not intended for climate purposes, but can be used for climate purposes. Or the natural world does the same thing. The natural world leaves records, signs that are about the climates of the past. If you're not comfortable with this word proxy, just to cut and paste in our definition of the word proxy. Proxy, I like the second definition here better. It's a figure that can be used to represent the value of something else. We don't actually know the temperature, but we know things from the natural world that can give us information about the temperatures. Historical records go back quite far in ways that we can then associate with climate anomalies. For example, the missionaries in South America were amazing at keeping records of their crops. The missionaries, especially like in Peru and Ecuador, were obsessive about keeping track of their records of their grape harvests and their pumpkin harvests and things like that. And that's very closely related in some parts of the world to climate features. There are other reasons why your pumpkin harvest might fail. There are other reasons why your grape harvest might fail. But they probably would mention that in their records. If they don't mention there was a large plague of locusts this year, but they do mention that they had this many pumpkins this year and they had that many pumpkins last year, well, that's information, and they can relate that using certain kinds of climate science to things like the temperature or the precipitation that the area had. And, for example, missionaries came to the Americas in the early 1500s. Within just a few years of Columbus's voyages, there were well-established missions in most of South America and Central America, and we have pretty good climate records from these guys. Just as another example of the kind of climate records that exist out there, this is a device called the nilometer. A number of these nilometers existed over the course of Egyptian history. Now, the most reliable nilometer observations come not from like the ancient Egyptian record, like the guys who made the pyramids. This is more like in the post-Arabic Muslim era, starting around 650 AD kind of thing. But observations do go farther back than that. And what a nilometer does is it measures the height of the Nile in a very precise way and a very systematic way. There's this pole that goes down a shaft right along the sides of the river, and they flood the shaft from the river, and then they can go down these steps and very precisely, in a very systematic way, tell you how high the Nile is. In Egypt, the Nile is the story about how they produce food. All food in Egypt is, in one way or another, tied to the height of the Nile and the irrigation that's possible. And in particular, historically, the seasonal flood of the Nile was very, very important, and to the ability of the Nile and the Nile Delta to produce food for the kingdom. And so ancient Egyptians were very obsessive about measuring such things, and even through them, like I said, since the arrival of Islam in the 600s AD, these observations are actually extremely good. Now, they're a measure of the height of the Nile River, but the height of the Nile River is associated with all the rain that falls upstream of the Nile River during the monsoon season, and that can be related to climate change and so on. And we actually have remarkably good records of the height of the Nile going back at least 13 centuries, and less good, but still better than nothing, records going back thousands of years. Cool. But then, of course, if we want to go back farther than that, we're going to have to start talking about ways that the natural world records the climate system, and the word we're going to use here is paleoproxies. A paleoproxy is a long-lived chemical or biological signal that has the climate system imprinted on it. When you're talking about the word paleoproxy, probably the best way to talk about paleoproxies is just to show an example. Probably the best example is to talk about ice in glaciers, or in ice sheets or whatever. This kind of ice provides interesting and useful climate data that goes way back to whenever that ice and snow fell. Now, this is a pretty cool thing because they do this with these ice cores. And again, you guys are environmental science majors. You probably were aware of the existence of ice cores, but climate scientists go out there with these special augers that can pull very carefully and under very controlled conditions. They can pull out these cores from ice sheets and so on. And most ice sheets and glaciers and so on are deposited in a yearly cycle where there is a winter season and a warm season, and in the warm season there's some melting and then refreezing when the colder weather comes. There's kind of an annual cycle to the depositing and the layering of the ice in these ice sheets. There's climate information in there. how thick these layers are, how what chemicals are trapped in these layers, what air pockets are trapped in there, etc. There's climate information in there if you can get it out. And that's why we have places like the National Ash Ice Core Center? I can't remember. This is the facility in Denver where they store these ice cores. I've actually never been there, but I have been to the very similar facility in Columbus, Ohio, the Bird Polar Research Center. And no pun intended, it's a pretty cool place. They have these big refrigerated rooms full of these long ice cores that different missions have gone to glaciers in the Andes or ice sheets in Antarctica or whatever, and they've pulled out these long ice cores, again under very careful, controlled circumstances, so there's no contamination or anything. And they can use different kinds of sensors and so on to study, like what we see there, that's some kind of image of, from some kind of scan of the ice, and you can see how there's structure to it. There's changes in the density of the ice, and there's little air pockets in the ice, and, depending on the kinds of tests you're doing, you might be measuring different chemicals in the ice or looking for particles in the ice. For example, identifying the timing, what year was this ice deposited. They might be looking for things like signs of a volcano that they know erupted in a particular year. If they can find that particular ash that was high in sulfur that came from that particular volcano, that helps us identify that this layer of ice was deposited in that particular year. This kind of ice core climate science is pretty amazing stuff. And these ice cores go back about 800,000 years. 800,000 years is about how fast the Earth recycles ice in the thickest, coldest places. It takes about 800,000 years from when ice is deposited in like central Antarctica to make its way to the shore of Antarctica and break off in the form of icebergs and things like that. Glaciers can be short, generally are shorter than that, but we have a pretty good record from ice cores going back about 800,000 years. Cool. And, from this we can find out, for example, that they can actually look through that ice core, and with like x-rays and stuff, they can find little air pockets that they can then, under very careful conditions, extract that air that has been trapped in that ice for as long as it's been since that ice was deposited. Potentially hundreds of thousands of years. Sometimes you hear the very cool term fossil air to describe that. This little trapped bubble of air that it has been in there under very controlled, very sanitary conditions for hundreds of thousands of years, and they can pull that out, and they can find out things like, for example, present-day concentrations of the greenhouse gases like carbon dioxide, methane, and nitrous oxide are clearly exceeding the ranges of and concentrations that were observed any time in the last 800,000 years. That's important information. The amount of carbon dioxide and so on that's in the atmosphere now is more than has happened at least in the last 800,000 years. That is valuable information to have when you're trying to understand the climate system. In the same way, the current rates of carbon dioxide, methane and nitrous oxide rises in the atmosphere are unprecedented compared to the highest resolution ice core data for the last 22,000 years. So if you can picture how that works with the ice sheets and how they deposit this ice every year, you can see that something similar is possible, for example, with regard to sediments on the floor of the ocean. Particularly as like a river dumps into the ocean, once the water slows down and moves out over the open ocean, sediment materials that are suspended in the river water start to sediment down to the bottom of the ocean and are deposited at known rates and so on. And those sediments contain all kinds of information that can be used to infer climate information. For example, they contain the skeletons of microorganisms, their little exoskeletons and so on. From that, they can determine things like the species of the different little critters that lived in the water at that time. As we're going to see, there's ways that they can learn things from this chemistry of what's in the shells of the little exoskeletons and so on. Before we do that, though, I do want to talk about corals. Corals are another way to get really good paleoclimate information. Corals grow in tropical oceans in kind of annual rings, similar to like a tree, and you can drill through a coral reef, which sounds horrible, but you can do, and extract what's effectively a climate record, as these corals have been building up on top of each other, and based on things like what species there are, but more importantly, what is the chemistry of the skeletons and so on left behind, you can do things like infer the temperatures of the water in which those corals lived. That's actually a really interesting story. Whether we're talking about oxygen trapped in the in little pockets in the glaciers, or whether you're talking about the water itself that is in the form of ice of the glaciers, or whether you're talking about oxygen held in the materials that make up the shells of the little critters buried in ocean sediments, or whether you're talking about the minerals in the coral, there are ways that we can use chemistry to tell us something about the climate under which those materials formed. Here's a happy little water molecule, H2O. That oxygen, which they're showing there in the red there, occurs quite naturally in two different isotopes. Now, in case you're not comfortable with the term isotope here, isotopes are when a particular atom has the same number of protons but a different number of neutrons in its nucleus. It's the number of protons that determines what element the material is, in this case oxygen, but the number of neutrons in there can vary. So it's still oxygen, but it has a different mass. So these are two different isotopes of oxygen, and in the case of on Earth, naturally oxygen occurs in two main isotopes. One is oxygen-16, which has 8 protons and 8 neutrons in it, and one is oxygen-18, which has 8 protons and 10 neutrons in it. Now, they are different. They are both oxygen. You can, if it's in the form of O2, you can breathe it. If it's the oxygen atom in a water molecule, you can drink it. But it does have differences. It has different masses, but it's still chemically still water. So some water molecules out there are made where it has an oxygen-16 atom as its oxygen in it, and some have an oxygen-18. They have different masses and different chemistries, despite the fact they're both water. Okay, I mean, they're both water in the sense you can drink it and fish can swim in it, but the appropriate equipment can detect the difference. Now, on Earth, oxygen-16 and oxygen-18 occur in known ratios. I'm drawing it here as being like out there in that open ocean water there. I have some, I've put some 16s and some 18s there, like those are molecules of oxygen, of water with oxygen-16 and molecules of water with oxygen-18. I'm drawing them like it's 50-50. It's nowhere near 50-50, but you get the idea. There's a known ratio of the number of oxygen-16s to the number of oxygen-18s. And one of the ways in which it makes a difference if it is oxygen-16 or oxygen-18 that's in the water molecules is water with an oxygen-16 evaporates at a different rate than oxygen-18 water does. In particular, at low temperatures, oxygen-16 evaporates a lot faster. The water that contains oxygen-16 evaporates a lot faster than the water involving oxygen-18. You could think of it as at low temperatures, those heavier water molecules that have the heavier oxygen molecule in them are like too heavy and slow to evaporate at those colder temperatures. Okay, so most of the evaporation that happens is the water based on oxygen-16. This is not the same thing, by the way, as heavy water. You may have heard of that term before. That's a different issue. In contrast, when it's warmer, the amount of oxygen-18 water evaporating increases. Both oxygen-16 and oxygen-18 increase, but oxygen-18 increases proportionally more. So there is information here in the sense of how much oxygen-16 and how much oxygen-18 there is in the form of water vapor at any given time. If it's mostly water based on oxygen-16, this evaporated under relatively cold conditions. If it has a higher enrichment of oxygen-18 in it, then it is a relatively warmer climate under which that evaporated. And this is going to be telling you then something about the global temperature. Now, the atmosphere doesn't store water vapor very long. In fact, the average residence time of water vapor in the Earth's atmosphere is only 10 days. These water molecules will very quickly go from being some kind of indicator of the temperature under which they evaporated to being water that falls onto the ground. So, for example, trapped in that ice core. So, that ice very quickly becomes a record of the temperatures of the water of the planet. That water that makes up that layer of ice came from all over the world. Okay? Because we don't know where that particular came from, but it is a representation of the water temperature all around the world. And if it's enriched in oxygen-18, it came from a warmer world. If it's depleted in oxygen-18, it is a colder world when that was deposited. And in fact, these things happen very precisely related to the temperature of the planet when the water evaporated. Any given molecule has a chance of evaporating, but over the course of the whole oceans of all the water molecules, the odds work out, right? We have a very large sample. We know the odds at which these things will be happening. And in the same way, there's like oxygen atoms that are incorporated with carbon into the shells of microorganisms, or with the minerals that make up the exoskeletons of coral when they build up the coral reef and so on. There's all kinds of ways in which we can use this sort of chemical isotope ratios of especially oxygen to determine the ratio, to determine the global temperatures at the time that these sediments were deposited or this ice was deposited or whatever. We can do that really far back if we need to. But another thing we can do is like tree rings. And tree rings actually kind of illustrate part of how we're going to be using this ice cores and stuff too. I mean, everybody knows about this use of tree rings to study climate. It's this subdiscipline known as Dendrochronology. Dendrochronology is this business of reconstructing past climates based on tree rings. And you guys know the story here, that when you cut down a tree, there are these rings, and each ring is a year's growth of the tree, and some rings are fat, representing a lot of growth that year, and some rings are very narrow, representing a relatively small amount of growth on the tree. On a living tree, the outermost ring is the current year's growth. You cut a core into the tree. They don't generally cut the tree down to do this. Because generally they do very, very old trees, right? It makes most sense to do a 10,000-year-old, well, I don't know if there's any 10,000-year-old trees, 2,000-year-old trees than to do a 20-year-old tree in your front yard or something. They cut down a core into the tree and they pull out the plug of all this climate information. The outermost ring, if the tree is alive, the outermost ring is the current year, and you can just work your way backward toward the center of the tree. In general, we can use dendrochronology to extend the record farther back than just living trees. Dendrochronologists go and find old wood, and they correlate the tree rings on that wood with living trees that overlapped. So like, for example, I remember seeing a study one time about dendrochronologists that were examining the timbers in Irish churches that had been built hundreds of years ago, and they would compare those timbers in the trees to living trees that overlapped the time when the trees that made those timbers were. And if they could find, okay, like here's 7 narrow rings in a row, then 2 fat rings, then 2 narrow rings, then a fat ring. Okay, they could find overlaps. Okay, then even though the living trees weren't all that old, the dead trees that made the timbers of the church then extended the record back hundreds of years farther. That's really cool. And we can do the same thing with ice cores, okay? If we can, for example, find a deposit of a particular volcano's ashes in the ice core at this height, and then that ice core is over, but we find that same ash in this level of this ice core, and we can look farther down in that one. By finding periods where those ice cores overlap and match up, we can extend the climate record farther. The same thing can be done with corals or ocean sediments or whatever. And if you're not actually worried about keying this climate information that comes from trees or ice cores or whatever so much to a specific year, then actually, like fossil tree rings are just fine, or ice cores that you can't necessarily date to a specific year. If it isn't terribly important to you to know that that ring comes from 722 AD, but you just know that this is the 8th century, and you can see, oh look, there was some really good years and there was some weak years, or all the rings are small or all the years are big. That can be good use information too. Same with like from your ice cores. Okay, we don't know exactly the years each of these layers of ice are, but we can see over this 100-year period it was warm throughout, and all these layers represent warm in the climate record. So if you don't need to key it to a particular year, you just want to know what was going on in that time period, then you can actually extend these climate records, whether they're from ice cores or dendrochronology or whatever, pretty far back. All of these paleo proxies can give you all kinds of information about the past. It just depends on how far back you want to go. For example, here's the last, 1,000 years or so of paleoclimate information from various sources. Different kinds of tree rings, boreholes, glaciers, etc. And if we're just trying to reconstruct the climate anomaly of the world, we can see that there's actually a number of things that have happened just in the last 1,000 years. The medieval warm period. The medieval warm period was a period in the, maybe from about 800 AD to about 1200 AD, where especially Europe was considerably warmer than normal. In fact, compared to its long-term average, in fact, comparable to present climate, which was relatively favorable in that time because of the general low standard at which most people left. Relatively gentle winters, relatively mild early springs, etc., were just useful if you're a Northern European peasant. Okay, it was a longer growing season, it was a relatively mild winter, it was useful. In contrast to the very bad news that came a couple hundred years later, the Little Ice Age. Again, the Little Ice Age is actually more a European thing than a global thing, but it had global impacts worldwide. It wasn't a true ice age, but it was a period when the climate was overall a few tenths of a degree colder globally, and more than that in like Northern Europe and Northern North America and so on. At that time, for example, it's the case, for example, that you've probably heard before, that at that time London would often have these so-called frost fairs, where if the River Thames would freeze, then there would be a big market out on the river, and they would have winter sports out on the river and so on. Now, it's a little bit of a myth that that actually happened all that much. Even during the Little Ice Age, most winters the Thames didn't freeze, but the Thames hasn't frozen over at all in 150 years or something like that. Okay, the fact that it ever happened back then was an interesting insight into the climate. People who study art history, for example, will find more depictions of winter scenes in that period than were in paintings before or after that, etc. We know about things like the extensive glaciers during that time period and so on. And when you start looking at these records, like these relatively small climate events like the medieval warm period and the Little Ice Age, you start realizing how astonishingly anomalous the current warming is. I mean, we are definitely as warm, if not warmer, than the medieval warm period. But we don't know these temperatures super duper precisely in the medieval warm period. And so we may be about the same, but we might be more already than the medieval warm period. If you go back longer than this, if you start trying to use ice cores and stuff to reconstruct the climate of the last, 12,000 years or so, you immediately get a sense that, well, first off, there's this whole crazy warming in the last 100 years or so, and the rate of that warming looks really scary. You also see that we had been tapering downward with temperature trend for about the last 5,000 years from, frankly, a kind of good place. Well, good in the sense, okay, in a judgmental, we'll say good place. That's called a climate optimum. It was a relatively warm period where, it's good and it's bad as to whether it's warm, but the right word is that they call that a climate optimum. But we were coming from a pretty warm place, and what's really interesting is we were coming from a really cold place before that. This is not the Ice Age. This is only about 12,000 years ago. The last Ice Age maximum was about 30,000 years ago. This was a weird little climate event on this diagram here called the Younger Dryas. If you're not familiar with the Younger Dryas, the Younger Dryas was a climate event that happened about 12,000 years ago and lasted, maybe 200-300 years. Relatively small little event. Where there were particularly cold years in North America and Europe in particular, where ice sheets started advancing again, glaciers were advancing. It was very, very cold for a few hundred years in North America and in Europe. It was due to a disruption of the thermohaline circulation, if you're familiar with that term, this big global system of ocean currents that redistributes heat around the world. In particular, the Gulf Stream broke down for a few hundred years during the Younger Dryas, and the Gulf Stream transports warm, moist water from the Gulf of Mexico up along the east coast of the United States and up towards Great Britain and Northern Europe and so on, which is a very large factor in moderating their climate. Especially wintertime climate would be a whole lot colder in places like Great Britain if it weren't for the Gulf Stream. Well, the Gulf Stream collapsed for a couple hundred years during the Younger Dryas. It's actually fascinating why it happened. It's widely believed to have been due to an ice jam that formed on the St. Lawrence Seaway and backed up this cold water in the Great Lakes. And when that ice jam broke, the flood of fresh cold water into the Atlantic stalled the Gulf Stream for a couple hundred years. Cool. But anyway, the Younger Dryas was on there about 12,000 years ago. A big climate event in world history. It's an example of what we call a stadial, by the way. I mainly was talking about the Younger Dryas so that we could introduce this word stadial. In paleoclimate context, the word stadial refers to a cooler period in the climate. Not really so much an ice age. What we mean is like a period of maybe a few hundred years where the climate is colder than the period on either side of it. That's in contrast to an interstadial. An interstadial is a warmer period with colder times on either side of it. And again, this isn't necessarily, we're going to see like the word interglacial in just a little bit. Interstadials are not necessarily very long, maybe on the order of a few decades to a few hundred years, but they are warmer than the periods on either side of them. If we look back across the last 4 million years, now here we don't have a temperature scale on this diagram. This is simply done in terms of ratio of oxygen 18 to oxygen 16. But knowing that as the ratio got bigger, it was warmer climate, and as the ratio got smaller, it was colder climate. You see that little dip right there? That little dip right there at the very end is the last glacial maximum, the Ice Age. Okay, that is when you hear about the Ice Age, and you're talking about mammoths walking across ice sheets in North America, and you hear about, all saber-toothed tigers and all that kind of stuff. Okay, they lived before that too, but the last glacial maximum, that's it, that little thing right there. But keep in mind, the scale is pretty big here. That was an Ice Age, a prolonged stadial with very low temperatures, continental scale ice sheets across North America, Europe, Asia, etc. And that's in contrast to an interglacial, which is a prolonged interstadial in which the continental ice sheets retreat or maybe even completely disappear as they are headed towards at the present time. That's it. That's that Ice Age right there. There have been lots of them. There have been many ice ages just in the last few million years. Paleoclimatologists have given up documenting counting them. Okay, if you go farther and farther back into the paleoclimate record, there's more and more and more ice ages. There's not the Ice Age, that's what we tend to call the most recent one, the last glacial maximum, which was only at its peak merely 25 to 30,000 years ago. It's hard to imagine that we had that big Ice Age that recently in geologic history. The last glacial maximum was a big one. Okay, many of the ice ages of the past were not as extensive as that particular one, but that was a big one. Ice ages typically last about 100,000 years, which sounds like a long time until you start thinking about geologic time. Like dinosaurs died out 65 million years ago, or the Phanerozoic is the last 500 million years. I mean, suddenly 100,000 years ago sounds like each of these little wiggles. All right. Going into an ice age tends to be a fairly gradual process that takes a few tens of thousands of years. 2-mile thick ice sheets across Minnesota don't just happen overnight. They take at least tens of thousands of years to happen. But the interglacials are shorter and happen fast. Glaciers retreat surprisingly fast. The actual transition from the maximum extent of a glacier to being in a full-blown interglacial period is on the order of centuries to a few thousand years. Which, when you consider again the fact that there are literally miles deep ice over places like the upper Midwest, you start realizing how much melting has to take place to make an interglacial happen. And it makes you wonder, how fast could we get rid of the ice sheets that remain, like Antarctica and Greenland? Oh, kind of gives you a warning shot here, doesn't it, about what could happen in an interglacial. Why do all these glaciers happen? What's the story here? Why do all these glaciers happen? Every ice age is a butterfly. Everyone happens for slightly different reasons. Everyone is a beautiful creation of its own. Most of these have been, certainly in the last few million years, have been determined to be caused by slight changes in the Earth's orbit. We're going to talk about orbital forcing of climate and so on when we get into the physics of climate, but Earth's orbit is actually chaotic on on geologic timescales. On geologic timescales, Earth's orbit becomes more eccentric, or becomes less eccentric, or the Earth becomes less tipped, or becomes more tipped, or whatever, or the solstices move, or the equinoxes move over geologic time in ways that are very hard to model or compute because of the intrinsically chaotic nature of an n-body orbit problem. We'll learn about that more in the next unit, but most of these can be traced back to, they can determine, oh, well, the Earth's orbit had changed in this way, and that is why ice sheets started to spread. Or the Earth's orbit had changed in this way, and that's why we were in an interglacial. Okay, most of the ones, at least in the last few million years, have been pretty well studied and we understand why they happened. And it was generally due to changes in the Earth's orbit, not, as the public often believes, to changes in the output of the sun. It is true that the sun's output does change. We monitor a property of the sun called the total solar irradiance, or TSI, and TSI is a measure of the total amount of energy that is received from the sun at the top of the Earth's atmosphere. The sun is a big flaming ball of nuclear fire, and it is not required to emit the same amount of power all the time, and to get the same amount of power to the Earth's orbit all the time. In fact, TSI varies a lot on a lot of different timescales, from billions of years to just a few days. There are changes that are due to things like sunspots. There are changes due to like the actual redistribution of the, I never know how to pronounce that word, metallicity of the sun as it changes hydrogen into helium. There have been all kinds of big changes in the sun, but the changes that we have observed in the last 140 years have all been really small, and not likely to be associated with the warming that we're seeing. In fact, since the late 1970s, we've actually continuously had satellites that were monitoring the flux of radiation from the sun, and it is true that in real time, the amount of solar radiation does vary slightly, but it is not related, it turns out, to the temperature changes that have been observed since the 1970s. We can determine how much the planet's temperature would have changed based on this slight change in the sun, and it is not related. Prior to the satellite data, we can actually get total solar irradiance data based on sunspot numbers. Sunspots were first studied in the early 1600s, and sunspots are well correlated to the amount of solar radiation at the top of the Earth's atmosphere. We can then take the period since the 1970s where we know the amount of solar radiation in the sunspots. If we have then just the record of the sunspots farther back, because early scientists were studying these things, we can actually extend the TSI records back to the 1600s. We can also do it based on radioisotopes that are trapped in like ice and so on. But depending on the extent of the solar activity, the sun produces different amount, the atmosphere produces different amounts of different radiocarbons and radioisotopes and so on. There are changes. We know that there are changes in the amount of output of the sun. There have been these periods called grand solar minima, where we know overall the total amount of energy emitted by the sun has gone down for like 50 to 100 years. The most famous of these is the so-called Maunder minimum. I'm going to show you a graph of the Maunder minimum in just a little bit, where for a period of about, 70 years or something like that, the sun emitted noticeably, had virtually no sunspot activity and emitted less radiation overall. And so we can take the records of sunspots that go all the way back to like the 1610s, and we can see, now, the sun does other things too. Notice that there's this well-known 11-year cycle to the amount of sunspots and so on. But there have been two main minima in the solar activity, the Maunder minimum and the Dalton minimum. And we know that there will be other ones as well, and we can model the sun and see that these things are happening and so on. But most estimates of these TSI changes, like between the Maunder minimum and the present maximum in solar activity, are on the order of like 0.1% changes in the solar flux, which is a real amount, and we need to take account of that when we're studying climate, but probably is not what is changing the climate on the very large amounts of energy stored on the Earth. The amount of energy that is the difference between the Maunder minimum and the present maximum is about the same as the difference in the amount of energy between the bottom of a solar cycle and the top of an 11-year cycle, okay? That we know the climate changes, and we know the amount of temperature change associated with the well-known 11-year cycle of solar activity. Maunder minimum should have only resulted in about the same amount. But just to give you a sense, here's about, about 30, 35 years of solar data from, I don't know if this is from satellites or if this is from, it's from NASA. Anyway, but you can see that there's this 11-year cycle to the total amount of radiance from the sun, and it varies quite a bit. I think the red curve is that it's a 31-day running mean. They used to actually do this at the Air Force Base in Omaha, where they were monitoring this, and now it's moved to a facility in Colorado Springs, I believe, or Boulder, I can't remember. But where they monitored the amount of solar activity and so on. But look at the X scale, the Y scale of this graph. I mean, if we're talking the flux of solar radiation, okay, meteorologists tend to use 1,366 watts per square meter as the solar constants. Well, look at our, I mean, almost all of our observations lie within a half of a watt per square meter of that. The total difference between the days when the sun is emitting relatively little radiation and the days when the sun is emitting relatively large amount of radiation is barely anything. Is that something we need to take into account when we're modeling the climate and so on? Absolutely. Is it likely that it's responsible for melting giant ice sheets? Excuse me. Probably not on these scales. Probably we would need bigger changes and longer lasting changes than what we're seeing here. On the other hand, temperatures and carbon dioxide concentrations, say over the last 400,000 years, are pretty closely correlated. If we reconstruct the temperature of the Earth based on, the isotopes in the ice and so on, and we reconstruct the amount of carbon dioxide that was in the atmosphere, that's a pretty good match. Looks like a big part of the global temperature is being related to the carbon dioxide concentration, whereas there's no particular reason to think the sun has been doing anything like this. Anyway, here's another diagram that shows you, how total solar radiation is changing over the last, few hundred years. And again, if you look at the scale here, we're talking on the order of like a half a watt, okay, per square meter. That's not very much power. On the other hand, over geologic time, the changes in solar irradiance are huge. Notice that this Y scale on this diagram here is billions of years before present. And if we go back, so if we define that at the present time, it's currently has like a unit of 1, a measure of 1 is the amount of radiation the sun's giving off. If you go back like 4 billion years, the sun gives off about 75% of that. So the sun is gradually increasing in its output as it moves through its life as a main sequence star. This is not global warming. I mean, yes, it's warming the planet, but this is not associated with the changes in the last 30 years, okay? This is over geologic time, over a course of billions of years. If we're still here a billion years from now, we have a serious problem on our hands as to how we're going to deal with this global warming. At this time, it's not a problem. As to how did life deal with this, I mean, there's been life on planet Earth through most of this time period. How did the planet of the Earth, I mean, if the planet is a warm and snuggly place for life right now, how was the Earth a warm and snuggly place for life when the sun's output was about 90% of what it is right now a billion years ago? The answer is life is pretty good at controlling the atmosphere and keeping it in a nice Goldilocks zone of temperatures by adjusting the carbon dioxide content of the Earth's atmosphere. By originally having much more carbon dioxide in the Earth's atmosphere and gradually pulling that carbon dioxide out, life has managed to keep the temperature of the Earth in a fairly narrow range. That becomes a problem in working on the assumption that humans will be long gone and we're not still burning greenhouse gases and fossil fuels and things like that. A billion years from now, there won't be enough carbon dioxide to keep removing from the Earth's atmosphere to keep the temperature from going up. But that's a billion years from now. We don't need to worry about that. Just to show you some of the other really cool things that have been found in paleoclimate, you may have heard of Snowball Earth before. At least once in Earth's history, about 600 million years ago, Earth pretty much froze all the way to the equator. It may not have been completely ice-locked at the equator itself. There may have been more like of a slushy ocean at that place. But basically, nearly the entire surface of the Earth froze back in about 650 million years ago. This is actually a really interesting challenge in the study of climate because it's hard to figure out how the Earth got out of this. I mean, once the Earth is a big white ball flying through space, it reflects almost all the shortwave radiation from, from the sun, and it's very hard to warm it back up. It's an active area of paleoclimate research to understand the processes that got the Earth out of Snowball Earth. But paleoclimate contains lots of information. It tells us lots of important things about the past. It tells us the last few decades of the 20th century were warmer than any comparable period in the last 400 years. Okay, so in the period of time that we have instrumented observations, it's definitely warmer than that. Probably since the medieval warm period, even though we don't have instrumented observations that far back, but we have good historical records then. Earth certainly has been colder than it is today, and Earth certainly has been warmer than it is today, but that's not really the point. The point is we live on a planet that's a particular range of temperatures. We have power grids and agriculture infrastructure and wildlife and so on that need the temperatures in this range. The present rate of warming is extraordinarily rapid compared to most of the changes in the paleoclimate record. In fact, there are relatively few events in the paleoclimate record that seem to have occurred on this time scale. There are such things as abrupt climate changes, but this is a really fast one. It is virtually certain that coming changes in the orbit of the Earth that are due to, changes in the, the precession of the Earth's axis and so on, will be unable to trigger glaciation in the next 1,000 years. You may have seen, actually, there have been recent studies that have even extended this and said 10,000 years, and some even said as much as 100,000 years. We have added enough greenhouse gases that even changes in the Earth's orbit that normally would be able to create a great ice age won't be able to now due to these changes. If we actually focus on what is the IPCC saying in AR5, they say point blank it is a fact that present day concentrations of atmospheric greenhouse gases like carbon dioxide exceed the range of concentrations seen any time in the last 800,000 years. Okay, we've got these ice cores, we know what the composition of the Earth's atmosphere was at these times, we've never been near it. They are not saying it's likely, they're not saying it's very likely, they're saying it's a fact. Okay, that is 100% certain, there is no disagreement on that point. With very high confidence, that's like 99% agreement, the current rates of carbon dioxide, methane, and nitrogen and associated radioforcing are unprecedented in at least the last 22,000 years. The key word here is rates. They're saying the rate at which we're increasing the carbon dioxide, we've never seen that before, at least in the last 22,000 years. They picked 22,000 because that's since the end of the since the passage of the last glacial maximum. Oh, that's a whole lot of scary to think that other things that can increase the amount of carbon dioxide and methane in the Earth's atmosphere, like volcanoes and stuff, have not ever changed it at the rate it's changing now. There is high confidence that the changes in atmospheric carbon dioxide play an important role in glacial interglacial cycles. We saw a diagram like that showed global temperature and global carbon dioxide. Heavens, that was a really good correlation. We have strong reason to see that there is a strong connection between global carbon dioxide concentrations and global temperature anomalies. There is very high confidence that the maximum global mean sea level of the last interglacial period, so we're talking like before the most recent ice age, the global sea level during that last interglacial period was, for several thousand years, at least 5 meters higher than present. And high confidence that it did not exceed 10 meters above sea level, above present. In other words, they're quite confident that in the last interglacial period, which looks a lot like the present climate, sea levels got between 5 and 10 meters above where they are now. Well, what did we say? We've actually increased sea level by like 8 inches. In other words, it can get a whole lot worse, okay? In a climate that looked an awful lot like what we're doing now, the amount of melting resulted in about 5 to 10 meters of sea level change. I don't like thinking about the possibility of the streets of New York being underwater or something like that. I always, poo-poo that kind of idea. If we had that kind of melting, we'd be getting into that range, though, where we'd start seeing water actually into current, infrastructure and so on, and not just during a storm or something like that. New temperature reconstructions and simulations of the warmest millennia of the last interglacial period show with medium confidence that the global mean annual temperatures were never more than 2 degrees Celsius higher than pre-industrial. Oh, that's a hard sentence to parse, but what it means is we aren't all that far now from the global temperatures that were seen during that last interglacial. We don't really like what that last interglacial period's climate looked like. Way too much melting, way too much increase in sea level, way too much warming, way too much extinction of species, and we're not that far from that now. This is one of the ways in which this number of 2 degrees C comes from. You may know that, a lot of what happened at the Paris Climate Conference was, let's keep the climate anomalies within 2 degrees Celsius. Yeah, we got to, because we don't like the last interglacial's climate, and we're getting close to that now. There is high confidence that an annual mean surface warming in the 20th century has reversed the long-term cooling trends of the last 5,000 years. Remember, over the last 5,000 years, we had been gradually cooling the planet due to orbital changes and things like that. We reversed it. 160 years of burning coal and we reversed that climate change. that probably means that we have a lot of power to make changes in how our planet works. And all of these ideas that climate change deniers have and so on, that we don't have the power to make changes in our planet, are probably not correct. This is all cool stuff, right? I love paleoclimate. I had a couple of classes in paleoclimate when I was in graduate school. I'd love to have a whole course here about paleoclimate. But this is a nice little overview of the paleoclimate chapter. Honestly, most of what we did in this actually comes from like the first few pages of the paleoclimate chapter in the textbook. Look through it. There's great stuff there. Paleoclimate is a fascinating discipline, and please let me know if you have any questions about this. This has been Dr. John Schrage.